In this video, the learner will use the geometric mean theorems to solve for lengths in right triangles. So when we have the altitude drawn from the right angle of a right triangle, we create those three similar right triangles. But instead of drawing out those three similar triangles, we actually have some shortcuts that we can use. The first one is the altitude theorem. So when we have the altitude drawn from the right angle of right triangle ABC, it cuts the hypotenuse of that big triangle into two sections. Here we have that altitude, which is h, and those two sections, x and y. What we're looking at is actually these two smaller triangles, and what we would normally do is compare those side lengths in those similar right triangles. So we would have x over h and h over y. Well, that tells us x over h, h over y, that h is the geometric mean of those two pieces. So without drawing those out, we know if we have the two pieces of the hypotenuse of the larger triangle and the altitude, we can just find the geometric mean of those pieces. So we have the piece of the hypotenuse, so in this case one of those is x, over that altitude equals that altitude over the piece of the hypotenuse. You're using the pieces of AB to form ratios with that altitude. The other theorem is the leg theorem. This time we're looking at the legs of that larger triangle. What we're really doing is we're still comparing those three similar triangles, but we're trying to do it in a faster way. So again, when an altitude is drawn from the right angle of a right triangle, the hypotenuse is separated into two segments, x and y. Notice these become leg lengths of the two smaller triangles. The length of a leg of the bigger triangle, okay, so like B or A, is the geometric mean between the length of the whole hypotenuse and the segment of the hypotenuse adjacent to that leg. So let's look at what this looks like. We have our larger triangle, ABC. Let's compare it first to that middle triangle. What we're doing is we're saying we can compare the hypotenuse and longer leg and hypotenuse and longer leg. Let's look at where those fall on this bigger picture. We have C, which is the whole hypotenuse of that larger triangle. That's compared to the hypotenuse of the smaller triangle, which in the whole picture is a leg of the larger triangle. Notice A is also the leg of triangle ABC. So we're saying C is to A as A is to Y. In other words, A, the leg, is the geometric mean of the whole hypotenuse and the piece that it corresponds to. Notice that Y in this picture here is on the same side of the diagram as A. So we have C over A equals A over Y. We're sticking to that side of the diagram. Now we're going to compare the larger triangle to the smaller triangle. So we're not using this middle one at all. Let's go ahead and get rid of it. So we have the larger triangle and the smaller triangle that we're looking at. Because we're using the leg theorem, we're comparing the length of the whole hypotenuse to the leg, and then the hypotenuse of the smaller triangle to its leg. So we have C over B equals B over X. So B is going to be the geometric mean of the whole hypotenuse and the piece that it corresponds to. Again, notice that X is on the same side of the diagram as the leg that it corresponds to. So we have the piece of the hypotenuse on the same side of the diagram. So we have the whole hypotenuse over the leg and the leg over the piece of the hypotenuse that corresponds with it. So let's look at a review of the geometric mean theorem so far. We have our altitude theorem, which says that the altitude is the geometric mean of the pieces of the hypotenuse, x over h, h over y. Piece of the hypotenuse over the altitude equals altitude over piece. Then we have our leg theorem, where we have the whole hypotenuse over the leg, and then the leg over the piece that it corresponds to. So c over a over y. Or if we're looking at the other side of the diagram, c over b equals b over x. The leg of the big right triangle is the geometric mean of the whole hypotenuse and the piece that it goes with. The leg of the big right triangle A is the geometric mean of c and y. B is the geometric mean of c and x. So let's look at a couple of examples. We've actually done these examples in class. So we had this example and this example where we had to draw out the three triangles and then use similarity. Now what we're going to do is use the theorems. So for x, notice that x is a leg. We have the pieces of the hypotenuse. So we're going to be using the leg theorem. So we have a leg, and we have the pieces of the hypotenuse. The piece that corresponds with x on the side of the diagram or on the side of the altitude is 8. So we have hypotenuse over leg equals leg over piece. That's a way to remember how to use the leg theorem. Well, the whole hypotenuse of the big triangle is 33. We're going to be setting that up in that ratio. Hypotenuse over leg, the leg we're solving for is x, equals x over 8. And now we solve the proportion. X squared equals 264, and then 2 root 66 is our answer. For y, y is the other leg of that larger right triangle. So again, we're going to be using the leg theorem. Hypotenuse over leg equals leg over piece. So we have hypotenuse is 33 over y, which is our leg of our right triangle, equals y over the piece that it corresponds to. Notice that y is on the same side of that altitude as 25. So 25 is the piece that we use. Now we cross multiply and get y squared equals 825. Square root both sides, and we get 5 root 33. For z, z is the altitude of the right triangle. So we're going to be using the altitude theorem. So we have piece over altitude equals altitude over piece. The pieces that we're referring to are the pieces of that hypotenuse. So here that will be 8 and 25. And that altitude will be the geometric mean of those two pieces. So 25 is to z, as z is to 8. Cross multiply, we get z squared equals 200, and so z is 10 root 2. Okay, let's take a look at the other example. For x, x is one of the pieces here. It's a piece of the hypotenuse. So if we want to solve for one of the pieces, we know that we can either use the leg theorem or the altitude theorem. However, notice we don't have the leg that it corresponds to, but we do have the altitude. So let's use the altitude theorem, which says piece over altitude equals altitude over piece. So 12 is going to be the geometric mean of the two pieces of the hypotenuse of that right triangle. That's what the altitude theorem says. So we have x is to 12, as 12 is to 9. because the piece is the x, the altitude was our 12, and the other piece of the hypotenuse was 9. Cross multiply and we get 9x equals 144, so x equals 16. For y, we now know that x is 16, so we know the piece that y corresponds to for the leg theorem. So we have hypotenuse over leg equals leg over piece. The whole hypotenuse will be our x value 16 plus the 9. So the whole thing will be x plus 9, which will be 25. So x plus 9 over y equals y over 16. That becomes 25 over y equals y over 16. Cross multiply, we get y squared equals 400. Square root, and y is 20. For z, z is the other leg of the right triangle, and 9 is the piece of the hypotenuse that corresponds to it. It's on the same side of that altitude as z. So we're going to be using the leg theorem, which again is whole hypotenuse over leg equals leg over piece. So we have hypotenuse over leg equals leg over piece. We know that the whole hypotenuse is x plus 9, and our x was 16, so we know that's 25. The leg that we're trying to solve for is z, and that's equal to z over the piece of the hypotenuse that corresponds with it. So 25 over z equals z over 9. Now cross multiply, and z squared equals 225, so z is 15. In examples 1 and 2 here on your own, I want you to solve for x, y, and z using the geometric mean theorems.